A hearty good morning, everybody, and welcome back to Calc 3. Plan for today is we're going to finish our discussion of Standard 4, mostly focusing today on interactions between lines and planes in R3. I've got my next office hours on Monday in the hour before class and from 2 to 3. As far as homework goes, Standard 4 quiz is going to be on Monday. So, might want to take a look at that. I've also, on Blackboard, just as a reminder, posted practice problems for Standard 4. Encourage you to give those a try, and feel free to contact me over the weekend. Let me know, send me an email or something if you have any questions about those. Anybody have any questions or comments before we get started today? Okay, got a few quizzes to pass back from last week. So let's see, Olivia. Jack. Whit. Avery. John. Richard. Lauren. Jacob. And okay, so before we dive into the math, question. To a mathematician, which is better, eternal bliss or a ham sandwich? Mathematician, ham sandwich is better. Why? Because a ham sandwich is better than nothing, and nothing is better than eternal bliss. Therefore, by the law of transitivity, ham sandwich is better than nothing is better than eternal bliss. Ham sandwich has got to be better than eternal bliss. Okay, so just to start off with a quick recap of the last couple of classes. On Monday, we talked about how to find lines in Rn using parametric equations. We said that if you have a line that happens to pass through this point P0 with coordinates B1, B2, B3, and if your line has slope vector A, then this R of t equals AT plus B, just sort of like the y equals AX plus B, gives us a form of the line, where if we split it up into individual coordinates for X, Y, and Z, we get what you see there. A plane, on the other hand, we define to be the set of all points P, such that if you have some fixed point P0 and a normal vector n that sticks out of P0, a plane is just the set of all points P where the displacement vector from P0 to P is orthogonal or perpendicular to this normal vector n sticking out of P0. So in essence, n is basically perpendicular or orthogonal to everything in the plane. And at the end of class last time, we had worked on this problem where I asked you all to help me find an equation for a plane that passes through a point P0 that is parallel to these vectors v and w, 2, 4, 1, and negative 1, 0, 2. Meaning v and w, if you place them to start at P0, would happen to be points that would be vectors that lay entirely inside of the plane. And the way we found that is we had to do some work to first of all find what a normal vector could be. We took the cross product of v and w to get our n. Found n was 8, negative 5, 4. And then we plugged in our normal vector and displacement vector from P0 to an arbitrary point x, y, z in our plane. We took the dot product, set it equal to 0, did some algebra, ended up with the formula 8x minus 5y plus 4z equals 36. And I wanted to mention this because I want to start today's class by talking about a new way to find equations for planes and see if it's any easier to find an equation for a plane in this context for this particular problem using our old approach versus our new approach, what we're going to be doing today. And to start off, I want to talk about how to find planes with parametric coordinates. So the way we had to find planes was just using this dot product formula, n dot p naught p is equal to 0. But there's another way that you could actually define a plane without needing to know anything about the normal vector at all, and that's using parametric coordinates. And here's how it goes. We're going to let pi be a plane containing point p naught, which is going to be equal to c1, c2, and c3, in parallel to non-zero, non-parallel vectors a and b. So in other words, we're going to assume we have some plane like this, where p naught is a point in our plane, and a and b are going to be vectors that if you were to place them to start at p naught as displacement vectors, a and b would lie entirely inside of our two-dimensional plane. Then we can find a parametric equation for our plane with the following formula. Parametric equation, x of st is equal to p naught as a vector plus t times the vector a plus s times the vector b. So in other words, if you wanted to write this out using x, y, z coordinates, you could write it as x of st is going to be c1 plus t times a1 plus s times b1. Y of st is c2 plus t times a2 plus s times b2. And z of st is c3 plus t times a3 plus s times b3. And that is going to give us a way of defining our plane using the same sorts of parametric coordinates that we did in defining lines. But looking at these parametric equations, can anybody tell me how do these equations look different than the equations for lines looked? Where the line equations, as a reminder, was like x of t equals a1t plus b1, y of t equals a2t plus b2, z of t was a3t plus b3. What mathematically makes our parametric equation for a plane different than the ones for a line? Ellen? Exactly. Yeah, here with lines we had a single slope vector, a1, a2, a3, that we were multiplying by this variable t, and said if you travel some amount t, doesn't matter how far, along this slope vector a, starting at our base point p naught, we would always get a point on our line. So that a1, a2, a3 gave us the slope vector for our line. If you use the parametric equation for a plane, you actually get two slope vectors. The a1, a2, a3, and b1, b2, b3 are both going to be slope vectors. Because if we were to start at some point in our plane, like say p naught, or this is just giving us our p naught coordinates, c1, c2, c3, if you traveled some amount in the direction of A, or in its opposite, and then if you traveled some amount in the direction of B, or its opposite, so you could go maybe to like here, followed by to here, maybe back this way again. If you travel along A any amount, or along B any amount, as long as you're starting in your plane, you're always going to still end up inside of your plane. And so we end up where a plane, at least parametrically, is essentially the same thing as a line, except it has two different slope vectors that you can travel along and still end up inside of your plane. Whereas with our line, starting at the point b1, b2, b3, we only had a single slope vector that we could travel along in either direction and still end up on the line. With a plane, we sort of have two different directions, which are going to correspond to the two independent variables t and s, that we could travel along this slope vector a or this other slope vector b that would allow us to still stay inside of our plane. So let's do a specific example where we work back through the exact same question as last time, and we wanted to find an equation for the same plane, 8x minus 5y plus 4z equals 36, except this time, let's do it using parametric coordinates. Because using parametric coordinates, I think might end up saving us some time here in going through this process. So, in this problem, we were given a base point, P naught is equal to 2, 0, 5. We're given two vectors that we want to lie inside of our plane, v and w. Our v was 2, 4, 1. Our w was negative 1, 0, 2. And so what we end up with is a single equation in terms of two variables, s and t for our plane, where since v and w lie inside of our plane, they can take the form of the a and the b from our definition over here. So we can actually write this out as being p naught as a vector plus of independent variable t times our vector v plus independent variable s times our vector w, which we could write as being 2, 0, 5 plus t times the vector 2, 4, 1 plus s times the vector negative 1, 0, 2. So if we wanted to look at the individual coordinates of little x of s and t, little y, little z, that'll give us points in our plane, what could our formula for little x of st look like here? If we were to basically combine all three of these vectors into a single vector and write out that first coordinate, the x coordinate of this vector that we would get if we multiplied out and added together, what would we end up with for our x? Yeah.
2 plus 2t minus s.
We'll have a 2 plus 2t plus s times negative 1, or minus s. I like it. So here's a 2 plus 2t minus s. How about for our y coordinate? We're going to take the middle coordinate of what we would get if we combined all of these vectors into one.
It would just be 4t.
We'd have a 0 plus a 4t plus a 0s. I agree. I think it comes out to just y of st is 4t. No s is needed there because our s is getting multiplied by 0. And finally, how about our z coordinate?
Plus t plus 2s.
We'll have a 5 plus a t plus a 2s. And there we go. Parametric equations for our plane. Now, if you just wanted to find a single point on your, if you wanted to find some points on your plane, you could just plug in values for s and t, and no matter what you plugged in for s or what you plugged in for t, you'll always get a point on this plane right here. So if we were to plug in s equals 0 and t equals 1, for instance, we would get 4, 4, 6, for instance, would be a point on our plane. Just like with our parametric equation for a line, you could plug in anything you wanted for t, and you would always get something on that line. Here, you could plug in anything for t and anything for s, as long as you're consistent and use the same s and t for all three equations, and you'll always get a point on this two-dimensional plane. So question. Which of these is easier to come up with? The 8x minus 5y plus 4z equals 36 from last time? Or this set of parametric equations here? In your opinion, this is an opinion question. Which involved less work, would you say?
Parametric equations.
Yeah. We only needed to go through all of this stuff. Whereas, well, I didn't write out all the work we needed last time for all this, but we had to take a 3x3 determinant to find this normal vector. We needed to do some dot products, multiplying out, some simplifying in order to get to 8x minus 5y plus 4z equals 36. This is actually, I think, easier to come up with in this setting. Owing to the fact that if we're given this information to start with, two vectors that lie in our plane, if they were to start at P0, it's a lot easier to use parametric coordinates to come up with an equation for your plane. Because if you have a point in your plane and two vectors in your plane, in this case v and w, you just plug them right into this formula here, and voila, there's your parametric equation for a plane. What would be a different type of problem, though, that might be easier to use this standard form of a plane instead of the parametric form? So in other words, what would be one way that we could be given some information and asked to find a plane that would make it easier to find the standard form of that plane rather than to find the parametric form? So in other words, if instead of knowing two vectors that were parallel to our plane, like v and w, what could be some other piece of information about our plane that we could be given that would make using this approach a lot easier? Yeah?
If we're given a normal vector?
Yeah, I agree. If we're given the normal vector, then I think this approach is actually easier because we could just say, oh, we're given a normal vector in our point, groovy, plug them right into this dot product, and there you go. And do a little bit of simplifying. Whereas if all that we're given is a normal vector to our plane, a parametric approach is harder because we would have to first find two vectors, v and w, that are both going to be orthogonal to that normal vector, which involves a bit of extra work. So if we're given this v and w that are parallel to our plane, I think it's easier to use parametric coordinates. But if what we're given instead is the normal vector, then it's a little bit easier to go through and just use the standard form of the plane. Any questions or comments about planes in their standard form versus parametric form? Okay, so let's move on then. I'm going to talk about we've talked about what it means for two lines to be parallel to each other. Is two lines are parallel if they happen to just have the same slope vector, or slope vectors that are scalar multiples of each other. Let's ask now, what do you think has to happen in order for two planes to be parallel? So let's say we have two planes, pi1 and pi2, that happen to look like this. They're never going to intersect. They kind of have the same formation on top of each other, like so. So basically, think of like two pieces of bread in a sandwich. where your two pieces of bread go infinitely far in either direction, so you can always have more sandwich, no matter how hungry you are. I shouldn't be making these references right before lunchtime. Let's try to do this a little better. It's a little better. So let's say we have two planes, pi1 and pi2, and we want to say what would be a condition we could put on those two planes that would make them parallel. So let's say we have a p0 here and a normal vector n, and let's say we have another point, p1, and another normal vector, and we'll call this one n1 and this one n2. We wanted to say that pi1 and pi2 are parallel planes what would be a condition that we could put on the individual parts of pi1 and pi2 that would cause them to be parallel like this, kind of be oriented the exact same way? Ever? Bingo. If their normal vectors are parallel to each other, then the two planes are parallel. Jackson, Emily, is that what you were going to say? There is one other condition, though, that would also allow for the two planes to be parallel in the same way, even if their normal vectors are not exactly parallel to each other. What else could the normal vectors be that would also allow for this? If the normal vectors are anti-parallel, meaning you had a scenario like this, then the two planes would also still be considered to be parallel. Because whether you take normal, because once you have a normal vector, you can always just take the negative of that normal vector, or any scalar multiple really, any non-zero scalar multiple, and it'll still be normal to your plane, something that would still work as a normal vector. That's something we talked about last time. So if your normal vectors are parallel or anti-parallel, then the two planes are going to be considered to be parallel. So, for instance, if we had a plane that was given by 2x minus 5y plus 6z is equal to 10, what would be another plane, a second plane, that we could say is parallel to this one? This 2x minus 5y plus 6z is equal to 10. Anybody think of a plane whose normal vector would be parallel or anti-parallel to this one? Avery? Negative 2x plus 5y minus 6z. So would you say these two planes are parallel? Rest of the class? I'd actually disagree. Well, technically I agree. My problem with your answer is I would say these are the exact same plane. Because any point satisfying this top equation will have to satisfy the bottom equation, and vice versa. Technically, you could say a plane is parallel to itself because its normal vector is parallel to itself because it's a scalar multiple of it, but what can we do to this equation that would make it a different plane that's still parallel to the original one? Or? Yeah. We could just keep this same stuff, but then just change the constant at the end. So we can make that a positive 10, or 110, or 110 times pi, or the square. I'll stop now. as long as this constant term at the end is anything other than negative 10, this is going to give us a different plane than the original one. But they will still be parallel because the normal vector of this one, which is 2, negative 5, 6, is anti-parallel to the normal vector of this one, which is negative 2, 5, negative 6. So these two planes are not the same plane, but they are going to be parallel to each other because their normal vectors, in this case, would be anti-parallel. Any questions or comments?
We do one where it's in parametric form instead of standard.
Yeah, sure. We can do a quick example. We can do a quick example of parametric form. So let's say, what is this? So let's say we were given this equation for a plane. X of st is equal to, I don't know, 1, 2, 3 plus t times the vector 4, 0, 5 plus s times the vector negative 1, 2, 8. What would be another plane that we could say is going to be parallel to the original one? This one's a bit trickier because here we're not given an explicit normal vector that we can see immediately from looking at this equation. Huh?
This is kind of shocking. Can you read the slope vector
To just have a different p naught but leave these two vectors the same? I think we can. Yeah, so let's see. How about this? 1, 2, 99 plus t times 4, 0, 5 plus s times negative 1, 2, 8. If you have the same vectors v and w, what did I call them in the original thing? A and b, but a different starting point. If we graph these, I'll call this one x, this one pi 1, and this one pi 2. If we graphed pi 1, we'd end up with something like this, where we have a p naught point here, and a vector a, and a vector b sticking out of p naught. If we wanted to graph what pi 2 would look like, if we picked a different starting point, like say down here, so if this is p naught, this can be our p1, and then looked at the same plane, the same two vectors, a and b, but starting at a different point, then the planes that we would get would in fact still be parallel like this. They have the same orientation in space, but one is kind of, I don't know, above and to the left of the other. So yeah, that would be a great way to find, if you're given a plane in parametric coordinates, something else that's going to be parallel to it is to just pick a different starting point, but use the same A and B as you did with the first one. There's one caveat to that, is that you have to make sure whatever point P1 you pick is not going to be a point in pi 1. Because if P1 is a point on pi 1, like say over here, then these two things would come out to the exact same point. And it can be generally a bit tricky to talk about, is this point P1 in this plane or not? But once you know you have a point not in this plane, just change your starting point to be that new point, and you can keep the same A and B slope vectors. Any other questions? Alright, so we've talked a lot about lines. We've talked a lot about planes. Let's do a problem where we're using both a line and a plane. So the next question I want to ask is, if we have a line and a plane, can we find the point at which the line and the plane intersect? So, in other words, where does the line, whose equations are given by x of t is t plus 5, y of t is equal to negative 2t minus 4, and z of t is equal to 3t plus 7. Where does this line intersect the plane 3x plus 2y minus 7z equals 2? So we're assuming we're in a situation like this, where we have some line L, we have some plane pi, where is going to be the point where this line happens to cut through the plane pi? If there is such a point. Spoiler alert, there is. And I would like to find this point right here, where if we were to, that point happens to both be a point on our plane, 3x plus 2y minus 7z equals 2, and on the line x of t, y of t, z of t equals t plus 5, negative 2t minus 4, negative 3t plus... It's not negative, just 3t plus 7. So what do y'all think about this one? If we're given some, no matter what we plug in for t, we're always going to get a point on our line L here. And we'd like to be able to find the point that also happens to lie inside of this plane. Meaning we'd like to find a point xyz on our line where that xyz happens to satisfy 3x plus 2y minus 7z is equal to 2. What could we try?
It's kind of a shot in the dark, but could you?
I like shots in the dark.
Could you just plug in any number for t and then set the x coordinates equal to each other and solve for the variable? So like set, I plug in the number for now t plus 5 equals 3x, and plug in the number for t and solve for x, and then do the same thing for y and z, and let that give you a point.
Ah, I see. So basically, you want to find like t in terms of x,
Yeah.
negative 2t minus 4 is equal to 2y, etc.
Yeah.
I don't like this. Why don't I like this? I think the issue we're going to run into there is that we don't necessarily want to set the x, is that this is not giving us something right here that's a three-dimensional point.
Okay.
3x plus 2y minus 7z is just going to be a scalar value.
Okay.
It's just, so we don't have three separate components that are going to be equal to the x, the y, and the z in terms of that. I think if we were given our plane in parametric coordinates rather than in standard form, then what you just described would actually work out really well. So I'm glad you suggested it, but I don't think that approach is going to help us out too much right here. Because all we're really given is a single kind of scalar sort of equation that we're going to be able to work with. Good shot in the dark. So if we wanted to find a point xyz that made this equation come true, what sort of substitution could we maybe make that would allow us to end up solving for something? Solve for x, y, and z, or potentially solve for t. I'd like to be able to end up with some equation that we could just solve for a single variable. Agree?
I mean, you can plug in the x, y, and z values into the plane, right?
I think that's going to be the best approach to take, yeah. Because if if we know that these two intersect each other, that means that no matter what we plugged in, that we would have some expression we could plug in for t into this equation, where if we did that and set that equal to 2, we should be able to solve for the variable t. So we're going to substitute the parametric line equations into our plane equation. I'm writing EQN for equation because I'm lazy. And if we do that, what we'll end up with is we should get 3 times our x-coordinate, t plus 5, on our line, plus 2 times our y-coordinate, negative 2t minus 4, minus 7 times our z-coordinate, 3t plus 7, is going to be equal to 2. Because if we have a point on our line, it should have x, y, and z equal to this stuff. And if it's also on our plane, it should satisfy this equation as well. But 3 times the x plus 2 times the y-coordinate minus 7 times the z-coordinate should come out to 2. And if we look at this equation right here, I think this is something we can solve. What variable can we solve this equation for? In other words, what variable do you see showing up in this equation? Yeah, this is an equation in terms of t. We can find the value of t that will make this plane equation come true. So if we do that, we'll get 3t plus 15 minus 4t minus 8 minus 21t minus 49 is equal to 2. You need to keep in mind that the minus 7, the minus part will distribute to both the 3t and to the 7. Which, if we combine, we'll get 3 minus 4 is negative 1, minus negative 21 is negative 22t, plus 15 minus 8 is plus 7, minus 49 is a negative, let's see, 7 minus 49 is negative 42. And so if we add 42 to both sides, we'll get negative 22t equals 44, which we can solve and find that t has to be equal to negative 2. Meaning, if we were to have a point on our line that also happens to be a point on our plane, meaning it satisfies this plane equation, the value of t for that point on the line would have to be at t equals negative 2. So are we done? Is that going to be the answer to our question? Yeah, I see you shaking your head.
You have to plug the t back into the parametric equations for the line.
Yeah, we have to plug the t back into the parametric equations. Because right here, we can't just say, at what point did the line and the plane intersect? Oh, they intersect at this point, t equals negative 2. That's not a point, that's not a three-dimensional point, that's just a scalar value. So to find the actual point corresponding to this t value, we have to plug that point into our line. The line, which if we do that, we'll get x of negative 2 is going to be negative 2 plus 5, just replacing the t here with our negative 2, which will give us 3. Our y of negative 2 is going to be negative 2 times negative 2 minus 4, which is 4 minus 4 is 0. And finally, our z of negative 2 is going to be 3 times negative 2 plus 7, which is negative 6 plus 7 is positive 1. And so our point of intersection is going to be the point 3, 0, 1. because that's the point we get when we plug in -2 for t. And we know if we plug in -2 for t, according to this equation right here, that should give us a point that happens to lie on our plane, as well as on our line. So we know 3, 0, 1. We just found that that's clearly a point on our line, because that's what we got when we plugged in t equals -2. Is there any quick way that we could check to see if 3, 0, 1 also lies on our plane? Just to make sure we did everything correctly? We've reached the end of the problem, but it'd be nice if there's kind of a quick way to check, is this also going to be on the plane? Yeah, let's see if we plug this into the plane equation and see if it works out. And so it turns out if we do that, what we'll get is that, so this is just a check at the end, does 3, 0, 1 satisfy the plane equation? Well, if we were to take 3 times our x-coordinate 3 plus 2 times our y-coordinate 0 minus 7 times our z-coordinate 1, do we get 2? We're going to get 9 plus 0 minus 7. We do, in fact, get 2. So it does satisfy the equation 3x plus 2y minus 7z is equal to 2. So 3, 0, 1 is, in fact, a point both on our line and on our plane. Neato mosquito. Any questions or comments before we look at our next one? Yeah, Tim?
If the normal vectors were orthogonal, but like by the same coordinate, wouldn't the planes still be parallel?
Ooh, so basically, let's say if we had something like this, where our normal vector for pi happens to also be orthogonal to the slope vector for our line L.
Yeah.
I think if that would happen, what you would end up with is this equation has no solution. You'd end up with something like, I don't know, 3t minus 3t is equal to 6, which if you simplify, would just give you something that couldn't possibly happen, that has no solution. No matter what you plug in for t, 3t minus 3t will never be equal to 6. And so typically, if in fact the line and the plane never intersect, which is totally possible if n and your slope vector for L are orthogonal, then you just wouldn't get a solution here and you would say there is no point of intersection. So that tells us how we can find where does our line intersect our plane. A slightly more interesting question, though, what we're going to see on the next page is, what happens if we have 2 lines and we want to find where the 2 lines intersect? Cat, I keep wanting to swat this thing. So let's say this time, instead of having a line and a plane that we'd like to find intersection points for, we have 2 lines. And so the next question up is, do the lines L1, which is given by equations x of t equals t, y of t equals 3 minus t, z of t equals 2t minus 3, and the line L2, whose equations are x of t equals 3t minus 8, y of t equals negative t plus 5, and z of t equals t minus 4. Do these lines intersect at all? Because if we have some line in L1 floating around in 3 space, and another line L2 floating around in 3 space, what would be something we could do now to check, do these two lines happen to intersect each other? Which, this one I think is a little bit more challenging because there's not something nice like a plane equation you could just plug in x, y, and z into in order to solve for t here real quickly.
Have you set that equal to each other for each variable? So like t equals 3t minus 8, for example, and then solve for t and see if there's a t value that makes
Okay, so you're proposing we just try and set the x coordinates, the y coordinates, the z coordinates equal, and see if we can find a single value t that'll make all the coordinates match up. I like that. Let's try that out. See how that works for us. So we're going to set all coordinates equal to each other. So if we do that, for our x coordinates, we'll end up with the equation t is equal to 3t minus 8. For our y coordinates, we'll get 3 minus t is equal to negative t plus 5. And for our third coordinate, we'll get 2t minus 3 is equal to t minus 4. Okay, so if we wanted to check, can we find a t that makes all of these equal t, what should we do? Other than wallowing in despair. Tyler?
You can solve for t in each equation.
Cool. Where do you want to start?
Y.
Oh, I don't want to start with y. I don't want to get to the fun one quite yet. Let's start with x and then we'll do y, just to see what happens. Because you're right, y by itself will tell us something very interesting. So if we solve for the x equation, we'll get that t is equal to 3t minus 8. Which we subtract t from both sides, we'll get 2t. And if we add 8 to both sides, we'll get 8. Meaning, in order for the x equation to be satisfied, we'll need that t has to be equal to 4. And now, we can check and see if t equals 4 solves the other two equations. Well, for our y equation, we'll get 3 minus t is equal to negative t plus 5. And if we add t to both sides, we'll get 3 is equal to 5. Uh-oh. So what value of t is going to make 3 equal to 5? What kind of reality-breaking value of t could we plug in that would make 3 equal to 5?
No solution?
No solution. Certainly t equals 4 won't do it. Turns out no value of t will make this work out. So there is no value of t that will make our two y coordinates equal to each other here. So what does that tell us? So what does that tell us about the two lines? L1 and L2. L1 and L2 do not intersect. Alan, watch the video for this one because there's about to be a twist. Dr. Gerstle, what do you mean there's about to be a twist? I'm gonna pull this one down and just look at a graph and see if we can plot these and top plot 3D just to see what happens. Wiki, oh, it's on, duh. Wish this had a monitor so I could start plugging things in without waiting for the projector to turn on. Okay, projector's supposed to be on. There's supposed to be a very cool dramatic moment that's not working because the projector doesn't work. Talk amongst yourselves for a couple minutes while I get this working. Is this not?
Back to -2.
Oh, no signal. Why is this no signal?
Just navigate this here. Email your
Sorry, I should have logged in before class, but I ran out of time. Y'all can keep talking if you like. Okay, so we want a line. X of t equals t, 3 minus t, 2t minus 3. What? Why is there a j? Alrighty, I'm going to graph the two lines now, and I want to see what happens. So here's one of our lines. X of t is t, y is 3 minus t, z is 2t minus 3. And I'm going to graph another line, or the other line. X is 3t minus 8, y is negative t plus 5, z is t minus 4. Uh-oh. What's that? What's going on here?
They barely missed each other.
All right, let's zoom in. All right, there's no visual trickery going on where it looks like they hit each other. These lines actually intersect. And it turns out all of this algebra we did was correct. There is no solution to this system of equations. So what gives? How are these two lines able to intersect even though there is no single value for t we can plug into this line and another value of t we can plug into this other line that will make all the coordinates equal? It does have to do with t being an independent variable. Here's the twist. We don't necessarily have to have the same t for our left line and the same t for our right line in order to be able to get the same point. The twist is that there's actually, say, one value of t, t1, that if you plug into this first line, there's a different value for t, t2, that you can plug into the second line, that will happen to produce the same x, y, and z coordinates. So everything we did here, where we set all the coordinates equal to each other, doesn't actually work. Strike it from the record. We actually need to do something a little bit more sinister. We need to answer this question. Does there exist some value of t1 we can plug in to the first line and t2, a value we could plug into the second line, so that the same point x, y, z is produced? Because there's no reason why the value of t you plug into the first line and the value of t you plug into the second line to produce the same x, y, z coordinates has to be the exact same value for t. So this is the question we really need to answer, which means for our first line, if we write it out as x of t1 equals t1, y of t1 equals 3 minus t1, and z of t1 equals 2t1 minus 3, where all I've done here is I just took the original L1 and replaced t with t1s. And for our second line, L2, if we replace all of our t's with t2s, we'll get x of t2 is 3t2 minus 8. Y of t2 is going to be negative t2 plus 5. And z of t2 is t2 minus 4. Now we need to see, is there a value of t1 and a value of t2 for line 1 and a value of t2 for L2 that will make these equal to each other? And to answer that, now I think we can take and set up a system of equations where instead of everything just being in terms of the same t parameter, we're going to have t1s and t2s showing up. So we get a system of equations that ends up looking like t1, if we set the x's equal to each other, we need that t1 is equal to 3t2 minus 8. Our y coordinate is being equal, tells us that 3 minus t1 has to be equal to negative t2 plus 5. And z coordinates being equal tells us we'll need 2t1 minus 3 has to be equal to t2 minus 4. And if we can find a t1 and a t2 that'll solve this system of equations, then we'll know whether or not the lines intersect. If there is no t1 and t2 making all of these equal, no point of intersection. If we can find a t1 and t2, the lines intersect. So this one's a little bit trickier, because you can't just look at a single equation and solve for a variable, like we did in the original attempt. So, what should we do? Tim?
Well, since we know that t1 equals 3t2 minus 8, we can plug that in for t1 in the other equations.
Cool. So you want to use the substitution method for solving a system of equations, it sounds like.
Yeah.
And just rewrite either the y equation or the z equation to just be in terms of t2?
Yeah.
Cool. Which one do you want to plug it into?
Y.
All right. So we're going to substitute our x equation into the y, which will tell us that 3 minus our t1 expression, which is equal to 3t2 minus 8, should be equal to negative t2 plus 5. Which if we simplify, and now this is an equation that's only written in terms of t2. So if we plug that in, so if we simplify, we'll get 3 minus 3t2 plus 8 is negative t2 plus 5. Going to add t2 to both sides to get negative 2t2. going to subtract 11 from both sides to get 5 minus 11, oh gosh, negative 6. And if we solve this for t2, we end up with t2 is equal to 3. Is that correctly? Yes, t2 is equal to 3. So, according to Tim's approach, if both of the first two equations are satisfied, the x and the y equations, then t2 would have to be equal to 3. Cool, t2 equals 3. Where can we go from here?
Plug in 3 to any of the T2s.
Plug in 3 to any of the t2s, and for what purpose?
Try to find T1.
Solve for t1. Okay. Have one that you would like to plug it into?
Z works.
Z works. I like x better because x already has just a t1 by itself. So if we do that, we'll get t1, which is 3, 2 minus 8, has to be then equal to 3 times 3 minus 8, which is 9 minus 8, and will tell us t1 is equal to 1. So we have a value of t1 and a value of t2. Do we know that this t1 and this t2 satisfy the x, y, and z equations?
No.
No? Which one do we not know if they satisfy or not?
I mean, we just have to plug them back in and make sure that.
Yeah, we could plug them in and make sure.
But
Since we use the x and the y equations to solve for t1 and t2, we know t1 equals 1 and t2 equals 3 are going to satisfy these two equations. So let's check our third equation just to see. Because it may not be the case, since we didn't use the z equation yet, it may or may not be true that t1 and t2 satisfy this equation. I sure hope they do, or that graph I showed you earlier is nothing but witchcraft. So let's ask, does 2t1 minus 3 equal t2 minus 4? To answer that question, we would get 2 times 1 minus 3. Is that equal to t2's 3 minus 4? Well, negative 1 equals negative 1. 8. That third equation is satisfied. So now we know at t1 equals 1 and t2 equals 3, all three of our coordinates are going to be equal to each other for the two lines. By the way, at this step, if we had found that the t1 and t2 we found didn't satisfy this last equation, that would be a sign that there is no t1 and t2 that make all three coordinates equal, and then we would truly know that the lines do not intersect. The fact that this last equation is also satisfied tells you that the two lines do intersect. So how can we find the point of intersection? Cool. Which one do you want to plug into which line? Let's do it. I like it. Yeah. Let's start by plugging in T1 into L1. So for L1, we would get that x of, what's our T1? T1 is, what's our T1? T1 is 1. That would be taking x of 1, which would give us, well, just 1. Y of 1, which is 3 minus 1, which is 2. And z of 1, which is 2 times 1 minus 3, equals negative 1. That's going to produce the point for us 1, 2, negative 1. And technically, we're done. We don't need to plug in T2 into L2 unless we want to check our work, because we already know from the work we did up till here that at T1 equals 1 and T2 equals 3, the two lines are going to produce the same point. But I think it's good to sort of check. with the second line, just to make sure we did everything correctly. For our second line, if we were to plug in t2 equals 3, we get x of 3 is 3 times 3 minus 8, which is 1. Y of 3 is negative 3 plus 5, which is 2. And z of 3 is 3 minus 4, which is negative 1. We found our point of intersection. Sorry to have to trick you all like that. I was feeling devious, and I was curious to see what you all would come up with. And you all, don't worry, my earlier class was just as tricked as you. All right, we're out of time for today, and we're done with Standard 4. On Monday, we're going to start class with the Standard 4 quiz, and then we'll jump right into Standard 5. Start talking more about matrices. Have a good one. Have a good weekend.